Hello and welcome everyone to another video. This time I want to show you how to make this response graph that you can see in the background. There is a lot to see here. There are these points in the foreground and there is my SpectroBeam visualizer in the background, but there is also these gray outlines that show the response curve of the bandpass filters. It's not like the best visualization ever. It's a little bit edgy and kinda inaccurate when you go to the low end. There are definitely better methods of doing that, but I think it's a good starting point. And not only that, it's also a very good method. The method that I'm going to show you is a good method for understanding how to get filter responses in general from filters. And yeah, there is another method that produces even better results and that is also more efficient, so that is just more elegant in general. But I will not explain it in this video because it's more of a DSP thing, and I think for those kind of things you should go to the YouTube channels that are actually more about math. This one actually has the more crude method that is really easy to understand. So let's get started. And when you want to make a class for graphing the filter response, you probably start by just making a class that inherits from component and from juice timer. Yeah, and you let it have a rather slow update time, and every time it updates it should check if the parameters of the filter are still the same or if they changed, and if they changed then you want to update the thing. I also made it so that it doesn't react to mouse clicks, so that it can be a background thing. You can already see the first thing that I did, which was that I'm clearing an impulse buffer and then only putting the first entry to 1, and that actually makes it a so-called delta function. A delta function is just a buffer where the first thing is 1 and every other entry is 0. In the paint method I'm just drawing the response curve. The response curve is just a juice path. In resized, I'm checking if the response curve is empty, and if not, I'm updating the response curve so that it fits to the new size again. And in timer callback, I'm checking if I need an update, and if yes, then I'm updating the response curve and repaint. We also have these two functions here, and one of them is the need update method that was used here. So from outside of the filter response graph function, it has to be defined what exactly updates this thing, and also from outside it has to be defined how the filters are being processed. And as you can see, the filters are being processed onto the samples that are given to this method. This method also has the impulse and the number of samples. Then there are also some other buffers that will make sense later. Now you probably want to know, what does the update response curve method do? First of all, it resets the buffers, which clears the process buffer, that is the buffer that is given here. So by putting it back to all zeros, you can fill it with the output of your filter later. And especially if you have filters in parallel, it makes sense to just let this start from 0. Yeah, and I'm also clearing the so-called DFT buffer because we need to use DFT later in this process. Now the next thing you do is processing the filters, and at the end of this line, the process buffer is filled with something that resembles the characteristics of the filter. After you have done that, you have to apply DFT on whatever is in the process buffer, which looks like this. This is forward DFT method, and that will convert whatever is in the process buffer into something that resembles how much magnitude the individual bins of frequencies have. As you can see, at the end of this function, we again have something into the process buffer. Actually, I have to say, only this part is getting the DFT, and this part is getting the magnitude from the DFT. Anyway, let's go on. And then we have generate response curve, which is more of a graphical thing because it uses all this kind of stuff like get width and get height and stuff in order to create a new response curve. You know, the response curve starts at x0 and y, whatever the first entry of the buffer is, times height. And then yeah, it just goes on like that. If you want to know what's going on here, then I would like to encourage you to watch my last video that I uploaded about the SpectroBeam visualizer, because it was very similar stuff that went on there that is also happening here. And yeah, that's basically how this works. Now, you probably don't really know yet how this works because I was just very cryptic about saying this does something that reveals the character of the filter, like how does it do that? right? So let's go to the low level component. So basically the low level component is always where I implement the stuff, and this is the needs update function. I'm basically starting by defining a bool needs update false, and if somewhere in this method this is being set to true, then true is returned and else false. What I'm doing here is I'm going through all the individual lanes, and when I say lane, I mean all the different filters, lane 1, lane 2, lane 3, so every filter is represented by one lane, and I have 3 of them, as you can see. So I'm doing that with a loop because then I can get the parameters with an offset value. This is just how I managed to do that, so that in the end in these arrays I have the new parameter values and I can check if they have changed. As you can see, this is really just an array of floats with the filter parameters. Yeah, and if any parameter has changed, that is what is checked here, then this returns true. That would cause process filters to be triggered by the update function in the filter response graph. And this also works very easily. We're just looping through the lanes. Then for each lane, we get the offsets, the indexes, and then the filter parameter values. Then we create a filter on the fly and we're giving it the parameter values. Then we just apply the filter on the impulse and put that or add that to the sample buffer. We're adding that because we have parallel processing in here. Otherwise, we could just replace it. So as you can see, this is basically just running the filter on the delta function, on the function that only has one and else a bunch of zeros. And if you apply DFT on that, that gives you basically the information about the response curve. That's how easy it is. This method is easy, as I said, but it takes a lot of CPU. Like you can see that when I'm moving around with my mouse here, then I have a lot of frame drops. Of course, I'm currently in debug mode, so it's to be expected that you have frame drops. But you know, the resolution in the low end and low mids also gets very bad quickly, and you see here it already looks like I don't even have anything at all here, even though I know that's not true. It always goes up to 0. It just doesn't show it very well. You can basically get around that by just making the impulse longer. That's why I said when I use juice debug, I use 2 to the power of 10 and else I use 2 to the power of 12 as the size of the impulse buffer, and all the other buffers here as well. So that increases the resolution in the low end. I don't want to demonstrate that now, but it works. The problem is just then there's the CPU consumption of this whole thing also increases dramatically, and it still doesn't look that good. So the other method that I will not show you now because I cannot explain it well, there basically everything is better. So you might ask yourself, why would you use this method? First of all, because everyone can apply it. You don't need to know a lot about math. It's more of a practical method. It's a good learning opportunity because of that. And also it might be that you one day run into a filter where you don't have the transfer function, because the so-called transfer function is what you need to apply the better method. And if you don't have the transfer function, then you really have no other choice than evaluating the transfer function with this method in the crude way, because this way will always work on all types of filters, no matter how weird they are or something. It's just useful to have something like that, even though you might not end up having to use that a lot. Okay, I hope you enjoyed this video and learned something that you find valuable. See you!